All right, Dr. Pitcher back, and in this lecture we'll take a look at the concept of optical activity. Now, what is optical activity? Optical activity is the property of a substance being able to rotate plane polarized light. So we'll say rotates plane polarized light. Now, that's a little hard to explain exactly what plane polarized light is, but if you're familiar with polarized sunglasses, those are a special kind of filter, and a light wave is going to, let's go ahead and make some axes here, and here's my light wave. Now, oops, this is up and down in terms of the amplitude of the light wave in the plane of the paper. But I could add in a third axis here if I wanted to, and maybe I would have light that was like front and back in the plane of the paper. So I could have light that's up and down, I could have light that's front and back, I could have any kind of angle here. And we call that unpolarized light. If we shine unpolarized light through a polarizing filter, we'll filter out everything but one orientation, let's say the up and down orientation of the light. And I'm just going to refer to the figure 5.6 in the text. So let me just say C Fig 5.6. And let me zoom in a little bit here, and I'll talk about this figure and what's going on. Focus. There we go. It's not terribly well focused, but that's okay. You can see the objects here. We have our light source, there's a light bulb, there's our unpolarized light. It goes through a polarizing filter. Only the plane polarized light in the vertical dimension is gets through. It's then that polarized light goes through the sample. And this sample contains whatever organic molecules. If the molecules are optically active, they actually rotate the plane of the polarized light. So maybe at the end it's now in the horizontal. And then you can view this using another polarizing filter. So here's the observer with the eyeball. And that angle there, alpha, is going to be our rotation. Okay, our observed rotation. Now, why do some things why are some things optically active? Well, it has to do with the fact that light itself has a handedness to it, because there's an electric component and a magnetic component, and they're at right angles to each other. So there is a, if you remember like the right-hand rule from physics, there is a handedness to light, and so when it interacts with other chiral things, we get this optical activity. So you'll actually measure this in the Carvone's lab. All right, so let's take a look at some definitions. So let's see here. Should I want to be consistent here? So we'll have our angle alpha, and we'll just call it alpha d sub d, and that is the specific rotation. And that's actually, every substance will have a particular value for the specific rotation. And it's actually given by the following formula. This is also in in the text, but I do want you to be able to use this formula and calculate a specific rotation from the observed rotations that you'll see in the lab this week. So we have our observed rotation, and that's in degrees, and we're going to divide that by the path length, and that's in decimeters. I know, an odd unit. 1 decimeter is 10 centimeters, times the concentration. And the concentration is grams per cubic centimeter, or grams per milliliter. So that is alpha over L times C. Now, just like in UV vis spectrophotometry, when we use a 1 centimeter cuvette, so our path length is 1 centimeter, we're going to use a 1 decimeter sample holder. So that way we can just replace L with 1. C, the concentration, is again, it's in grams per milliliter. And if we have stuff that is neat, that is, it is a pure sample, no solvent present, we would use the density. So let's see here. For neat substances, so no solvent present, use density. So if we actually shine things through a more concentrated sample, we'd get a greater, we should see a greater rotation. If we have a longer path length, we would get a greater rotation. So you'll have these densities. I mean, I'll give them to you, and you can so plug those in and actually calculate a specific rotation for your sample or in the lab. Now, a couple more things to mention here. So this is our specific rotation, and let's see here. Let's say reporting optical activity versus chiral versus chiral configurations. Okay, so when we take a look at how we would report things for optically active compounds, we use either plus and minus, or little d and little l. That stands for dextrorotatory and levorotatory. The text mentions this. And this indicates the direction of the rotation of the plane polarized light. Now we have some other terms. You may see a small caps D and a small caps L. And some people just use capital D, capital L, but when you're actually, writing an article or journal article, paper, you would use the small caps D and L. This is the configuration, so I'm going to say the stereochemical configuration of a molecule relative to glyceraldehyde. Specifically L-glyceraldehyde. And then lastly, we have absolute configuration. And this is R and S, capital R, capital S. And this is the configuration of chiral carbons. And that's according to the Ingold pre-log rules, which will be in the next lecture video. Now these are different things. Optical activity, you measure that. And we've got the newer version of reporting at the older version. Relative configuration, D or L, is mostly found in biochemistry. For example, all naturally occurring amino acids, except for glycine, which is not chiral, but all naturally occurring amino acids are the L enantiomer. All naturally occurring sugars are the D enantiomer. Now, R and S refer to specific carbons. So if you have, let's say you had serine, that's an amino acid, so it's going to be L-serine if it's naturally occurring. The chiral carbon in serine may be S, it may be R. I don't know. I'd have to take a look at it. So these mean different things. Absolute configuration R and S is according to the rules that we'll talk about in the next lecture video. Relative configuration is when we compare our overall configuration of our molecule to a specific reference, which is L-glyceraldehyde. And then optical activity is something you measure in lab. You can't measure these in lab. Okay, little d doesn't correspond to small caps D. All right? So this should help a little bit with some of the experimental part of lab. And I do want to mention one thing, which is that enantiomers have identical physical and chemical properties, except when interacting with something chiral. So enantiomers, a pair of enantiomers, those should both have the same boiling point. If they don't have the same boiling point, then one's not pure. That's about all I could say about that. But enantiomers would have the same boiling point. They would have the same refractive index. They have opposite optical activities. If they're reacting with a non-chiral compound, then they're going to react the same. If they're reacting with a compound that is chiral, like let's say an enzyme. So if a chiral molecule undergoes a reaction catalyzed by an enzyme, then that enzyme is chiral. It's made up of L amino acids, so it's got to be chiral. And maybe the enzyme works on, the R enantiomer, but not on the S, something like that. We'll talk about that more in the next lecture video. All right, well, until next time, stay safe out there. Bye now.